Niels Bohr decided to try and explain the hydrogen emission spectrum. Specifically, when you use electricity to excite hydrogen, you only see 4 emissions in the visible region. There's the violet one at 410 nanometers, blue at 434, green at 486, and red at 656, but nothing in between. So Bohr's question was, why so few? Why don't we see a continuous spectrum? This must mean that the allowed energy levels for electrons in a hydrogen atom are restricted to only a few values. Bohr came up with a model that's kind of like a miniature solar system. Bohr thought that in an atom, the nucleus at the center was like a tiny sun, and then he said that the electrons could only exist in certain orbits, like planets, and the orbits are given by a single number. n equals 1 is the lowest energy orbit, n equals 2 is higher, n equals 3, n equals 4, and so on. So the electrons can exist in these orbits, but nowhere in between. Furthermore, he used the Rydberg equation, 1 over the wavelength equals 1.097 times 10 to the 7th inverse meters times 1 over n1 squared minus 1 over n2 squared, where n1 and n2 are the different energy levels, and n2 is always greater than n1. Using this equation, Bohr was able to show that the 656 nanometer transition, the red one, was from a transition from n equals 3 to n equals 2. He showed that the green transition was n equals 4 to n equals 2. The blue transition, n equals 5 to n equals 2. And the purple transition was n equals 6 to n equals 2. Now, this works great for hydrogen. Bohr got essentially a perfect fit for hydrogen. When he tried it with helium, not so much. In fact, the answers got worse and worse the more electrons he used. Where did Bohr go wrong? Well, it turns out that he was right in that electrons can only have certain energy levels, but he was wrong in thinking of electrons as being particles. Electrons are more like waves, just like photons. They're both waves and particles at the same time. So, an orbital is what's called a wave function. This is a surface within which you are likely to find an electron at a given time. This picture, imagine if you had a camera that could take a picture of an electron's position, and it snapped a picture every few microseconds. After it snapped several thousand pictures and superimposed them, you would see a dot for each time the electron's position was recorded. Here you see a spherical distribution of electron density. This is called an s orbital. Quantum mechanics gives rise to other orbitals. We'll look at that in the next video.